Mathematical modeling with ordinary differential equations has been used for a long time to model various phenomena in the natural sciences. An example is the model that describes the motion of the pendulum. The dynamics of the pendulum can be represented with time series, where the values of the model variables are plotted across time, or in a phase portrait. Phase portraits are, in practice, geometric representations of the trajectories of a dynamical system in the phase space. In this work, we are particularly concerned with dynamical systems that describe biological processes. Observing the geometry of the trajectories in phase portraits allows mathematical domain scientists to understand important dynamics of the systems and potentially of the underlying processes. However, in the biological domain, the systems can be quite complex, going beyond 2D. If the system is 3D, then the domain scientists often use frameworks such as MATLAB or Mathematica to generate static 2D projections of phase portraits, or sometimes static 3D phase portraits. For 4D systems, phase portrait analysis becomes challenging with simple 2D or 3D subspace representations. The juxtaposition of the 2D or 3D phase portraits provides limited insight, as certain complex patterns can be revealed only by considering the entire 4D space. Also, 4D space reconstruction has to be done mentally with requirements of spatial imagination. To this end, we created HyperLand. Represented as a tesseract, HyperLand comprehensively shows the morphology of the entire 4D space. In HyperLand, the trajectory of a 4D dynamical system is displayed inside a tesseract representation. In this way, we obtain the analogous of a 4D phase portrait. Apart from phase portraits, timelines that illustrate the temporal evolution of biological system variables are also provided. Several phenomena occurring along the trajectory can be observed easier if the entire 4D space is considered. Others can be seen easier in certain subspaces, 3D, 2D, or 1D. Therefore, it is necessary to access smaller segments of interest of the trajectory also in their distinct subspaces. Switches in the behavior of trajectory segments are important, but not always known a priori. The most straightforward approach to explore all available subspaces would be multiple coordinated views. In our case, this would require a significant amount of screen space, but it is also similar to the currently employed and suboptimal workflow with phase portraits. A mechanism to transit interactively across subspaces is required. We propose ManyLands to improve the current workflow of mathematical domain scientists specialized in analyzing 4D mathematical models of biological systems. With ManyLands, domain scientists can effectively navigate with continuous, seamless transitions across visual representations of trajectories in different subspaces. By describing the subspaces as lands, we accompany domain scientists along a continuous journey through 4D HyperLand, 3D SpaceLand, and 2D FlatLand. These are linked to 1D timelines. With ManyLands, domain scientists have a holistic view of the entire 4D phase space, can detect and explore switches in trajectory behaviors across subspaces. We offer an additional dissected view of trajectories with small multiple pictograms to serve as compasses for easy navigation across subspaces and across trajectory segments of interest. Finally, ManyLands supports the integration of hypothesis confirmation and knowledge discovery with an effortless illustration thereof within a common web-based framework. We will now demonstrate a use case as it was conducted by the domain scientists. This case involves the Olson model for the peroxidase-oxidase reaction, which is 4-dimensional. The Olson model is a chaotic attractor system. The 4D view of HyperLand can confirm at a glance the chaotic attractor behavior as denoted by the multitude of loops. By transients to 2D FlatLand and in particular to the ZW space, the trajectory comes repeatedly close to the origin and spends longer intervals of time there. With focus plus context on the 3D SpaceLand, the XZW and XYW subspaces are illustrated for further analysis. In XZW, the system is a chaotic attractor, while in XYW it is a transient. Practically, the system exhibits a slow motion and makes the long excursion in the XYZW space before returning to the 0ZW plane. Additionally, the initial part of timelines shows changes in speed denoted with the grayscale. The second part of timelines manifests periodic behavior, while in between a switching behavior can be also noticed. ManyLands has facilitated the analysis of the complex 4D dynamics of the Olson model, supporting a geometric analysis of the chaotic attractor and revealing its oscillatory behavior.